Good morning. Welcome to Parallelizing Scientific Python with Dask. My name is Jim Crist. Over here we have Martin Durant and Skipper Siebold. We will be presenting to you today. To start things off, can I get a hand count? How many people have heard of Dask before? Okay, most of everyone. How many people have used Dask before? Fewer hands. How many hope to use Dask after this? Awesome. Cool. So we have hopefully a painless install today. Everyone needs to go to this webpage. Make sure you do the HTTPS. It doesn't redirect. And then you'll see a big blue button, and I want you to click it. And that's it. The password is changed. Password is PyData. We are in the Dask tutorial folder. There's another tutorial going on next door, also taught by the Dask team, plus Min, talking about different Python parallelizing systems. Or not Min, Aaron, Amadea. And so we are parallel tutorials. So you're going to just be in the Dask folder today. We are going to start with Notebook 2, Dask delayed. So if everyone can just open that up. Can everyone read that from the back? Is that big enough? A little bigger? These are small screens. I want to be able to make sure everything's... Oh, I can do that, yeah. View, toggle header, view. Is anyone not at this page at this point? Okay, if you're not, hopefully you can get help from your neighbor, because we're going to start. So Dask is a parallel computing framework. There is a lot to it. It's used for many different domains. We're going to start from the beginning and try to work our way up. This is going to be by no means a comprehensive tutorial. We're just going to try to get you a taste of everything, and hopefully you can go from there. We hope our documentation is good enough. So we're going to start with some simple toy functions. Inc, which increments a number, and add, which adds two numbers together. These have a sleep in there to make them take some time so we can actually measure them. You could substitute in any complicated computation instead. If we run them in serial, so we increment 1, we increment 2, and then we add the results together, this should take 3 seconds. Each function takes 1. Combined together, they take 3. One of the tools we have in Dask is this function called Dask delayed. It's a pretty simple interface. If you're familiar with decorators, this will sit right in. But basically, delayed is a function which does two things. If you call delayed on another function, it makes that function lazy. It doesn't run immediately. It'll run later. And if you call delayed on data, say you called delayed on an array, it makes anything that touches that array lazy. It'll run later. So we're just going to take delayed from Dask, and we are going to wrap it around inc and call it on 1, wrap it around inc and call it on 2, and then wrap it around add and call it on the results. So if we time this again, it runs immediately. But it hasn't actually run. This is just building up a graph behind the scenes. To actually get Dask to run anything, you need to use the compute method. So if we take z, let's actually look at what z is. It's a delayed value. And we call compute on it. This is actually running it. And this time it took 2 seconds. Does anyone know why it took 2 instead of 3? Is it running X, Y currently? Yeah. So if we actually look at the graph here, so here's z is a delayed value. The visualize method is on all Dask objects. You can see the task graph that it's composed of. So here we can see we have incrementing one number, incrementing another number, and then we're going to add them together at the end. And if you were to actually try to do these, you can see these can be done in parallel. This task doesn't depend on any other tasks. This task doesn't depend on any other tasks. So if we have a thread pool or a process pool or some kind of worker, we can run those two at the same time. Any questions so far?
Sorry, I did get hold of the Dask tutorial, but I have a different Dask tutorial than
We're running in a distributed environment. You don't have to download anything. If you missed the start, hopefully you can get the URL from a friend. Otherwise, I'll put it up here for 1 second. It's in the Slack channel. Cool.
Yeah, we're in a specific branch for this session.
Yeah. So you'll just go to the URL in the Slack and push the big blue button. Password's PyData. Cool. All right. So here we're going to move right into an exercise. So here we're going to parallelize a for loop. So we have some data stored as a list. The sequential code is going to, I'm just going to start that. The sequential code is going to loop through the data. It's going to call inc on each element, and it's going to store them together in a results list. And at the very end, it's going to sum the results. You can see the total here. We'd like you to parallelize this using delayed. The code should look fairly similar, just adding the delayed call in strategic places. So we'll give you a couple minutes to do that. Discuss with your neighbor if you get stuck. All right, so if you click on the solution button here, you can actually see what the solution we're looking for is. So I'm just going to copy this up. All right, so looking at our previous code, up here, we looped through the data. We called inc on each element, and then we stored them together in the results. And then at the very end, we called sum on the results list. Down here, what we do is we call delayed on inc, and then call that on each element. We store that result in the list. And then at the very end, we say total is equal to delayed of the sum of that results list. So if we time that, it runs pretty much immediately. And if you look at the result there, total is a delayed value. And since it's a delayed value, we can look at its graph and see the familiar map reduce pattern here. We're calling inc on every element, and at the very end, we're summing them. And if we were to actually compute that, use the compute method, you can see it took about a second because everything was running in parallel. We have 8 elements, and I have 8 CPUs in my computer. So I can run one computation in each one. So we're going to move on to a slightly more complicated example. Oh, question? Yeah, it does. That's a question for further on, but we can talk about it now. So if instead of calling, just because I ran this before, this still exists, it's the list of delayed results. What happens if I call result or sum of the results? Does anyone have an idea what would happen here? Yeah, so delayed objects implement most operators. And so since sum is going to try to add every element, let's just see what that graph looks like. So you can see all the different pairs added together up in a chain. This doesn't actually get any parallelism. So it's important to think about exactly what should be delayed and what should run immediately. All right, moving on. Slightly more complicated example. We're going to add some control loop flow in here. So we have a function double, which doubles a number, and we have a function which checks if a number is even. And then we're going to have a new data list. This time, what we want to do is we want to iterate through the data. If the element is even, we want to double it. Otherwise, we want to increment it. And then we're still going to store all the results in the results list, and at the end, sum them together. So again, take some time, figure out how to delay this. You're going to want to delay some functions here, but not all of them. So I'll give you, I don't know, 3 or 4 minutes to do this. So without even looking at the solution, what should we delay here? Should I delay is even? No? All right, why not? Can anyone tell me why I shouldn't? Yeah, so it doesn't take time. Is x a delayed value or not? when we're iterating through. No x is real data, and we want to check if it's even. One thing about delayed values is you can't check their truthiness. We don't know what they actually represent. We don't know what is behind it. We just know that it exists at that time. We'd have to actually call compute to figure out if it's a true or a false value. So you can't delay them. Should I delay double? Yep. How about inc? And we already talked about delaying sum. So that again runs in 1 second, and we can look at its graph. And see, it's a similar MapReduce pattern, but this time we're only using certain functions on certain elements. Cool. So here we're going to parallelize something more complex.
So here's this situation where you have a new statement, control flow, in the middle of some code that you'd like to make parallel.
Mm-hmm.
So basically what you're telling us is if that's the case, you can't use Dask.
No. So you'd have to think about what you need to do. Maybe you want to wrap that if statement inside a function that's lazy. Where do you put, so here we're trying to build up a graph and we're trying to encode those Boolean decisions inside the graph. They've already been made at graph build time, but not at compute time. You could put them off until later. You could have a function double or inc that checks internally if an element is even and does one or the other. That make sense?
Yeah.
Cool.
I just have the feeling that there's going to be a fair amount of code that will fit that pattern.
Mm-hmm.
Could you like insert a compute in the middle?
Yes, you could. It will compute everything up to the graph that's needed for that element, but you don't necessarily. Often we find rethinking how you lay out your code, slightly moving things around, but for the most part, just adding in delayed seems to work pretty well for parallelizing existing code. And we'll touch on this later in the tutorial. So here we're going to move on to something that's actually a real world example. So this cell right here is just prepping some data you all have in your cluster. So that's extracting some flight data. This is the airlines data set. It's a set of all airlines travel in the US. I've filtered this down to just the flights in the 90s out of New York. So this is going to be stored as 10 CSV files. And so we can look at those here and see you have a file per year. So just to look more at the data, we can open that up with Pandas. Real quick, just for our understanding, how many people have used Pandas before? Okay. This isn't going to be terribly Pandas heavy, but just wanted to see what we needed to explain and what we could maybe assume some background knowledge of. Cool. So here we're going to be using Pandas read CSV to just peek at the first couple rows just to see what the data looks like. So this is just one file. This is just 1990. So we have some columns for year, month, day of the month. So that makes up the full date. Different things about departure time, whether it's delayed, unique carrier. Over here we have the originating airport. There's a Boolean column if it was canceled. We can see what the D types are based on that Pandas data frame. So you can see the year, month, and day are all stored as integers. And we can see what the originating airports were. And as I said, I filtered it down to just flights out of New York. So EWR, LGA, and JFK. On this 1 year alone, we can group by origin, take the departure delay, and take the mean of it. So the mean departure delay per airport for just 1990. What we'd like to do is we'd like to compute the same thing for all the files combined. And we'd like to do this without loading all of the files into memory at once. We'd like to figure out some way to do this sequentially, taking in a file, storing some intermediate, and at the end combining those intermediates together to get a final result. This is something that you could scale if you had hundreds of files and maybe run on your laptop without having to load all of the CSVs in at once. So here I have some sequential code for doing this. We're going to take a glob, so a glob string of all the CSVs in the NYC flights folder. So you can get all the file names. We're going to loop through the file names, read in each file, group by airport. We're going to sum all the departure delays by the originating airport, and we're going to count all of them, and then we're going to store all the sums, and we're going to store all the counts. And at the very end, we're going to sum all the sums, sum all the counts, and divide to get the mean. So if I run that right now, this should take, if I remember right, about 10, 15 seconds. Oh, I did not remember right. 4 seconds. And here we can see the departure delays, mean departure delay per airport for all of the 90s. What we'd like you to do is we'd like you to parallelize this code using delayed. There's a couple new things you need to know. One, delayed objects implement operators and implement methods. So if you have a method on the real-world object, what it will be once it's computed, you can call that method on the delayed object, and Dask will do the right thing. Two, we have a function called Dask compute. Oh. So from Dask import compute. This is similar to the compute method, but you can pass in multiple delayed objects. If you have 2 delayed objects and you call, delayed object 1.compute, and later you call delayed object 2.compute, if they share intermediates, if they say we have the sums and the counts, if they share intermediates, they're both going to compute those intermediates twice. But if you pass both of them to Dask.compute, so the compute function, they're going to compute them in the same pass. Dask will merge the graphs. Dask will only do each task once. It'll be more efficient. So using these 2 things, we'd like you to parallelize this existing code. I've copied it down here. You should just need to add delayed in a couple of spots and add a compute call. I'll give you a couple minutes to do that. A good question was just asked. Delayed plays well with existing Python structures. So if you pass in lists or dictionaries or sets, basically built-in objects containing delayed values, delayed will figure out how to recompose those. So if you call compute on a list of delayed values, you'll get back a list of the results that they represent. So you don't necessarily need to pass in delayed values just to compute. You can pass in Python structures containing them. Just to be clear, you may or may not need that here. All right, for the sake of time, we're going to move on. Just walking through this, where should I put delayed? Should I call delayed on read CSV? Yeah? Okay. Yeah, we want to delay data ingest. It's best to have Dask load your data rather than load it before and pass it to Dask. That can help minimize memory usage. Do I need to call delayed on group by? No, group by is a method. The DataFrame or DF is already a delayed object. Methods on delayed objects just work. Similarly, by origin delayed, so this works. By origin delayed, so that works fine. And we store all the results together in lists. Where should I call compute? There are 2 different places I can think of here. We'll start with one. You could say sums counts is equal to compute sums counts. Did anyone have this solution? All right, so what's happening here is we're looping through, we're getting all the sums, and then we're computing them, bringing them into memory, and then doing the sum here and the sum there and the divide all immediately. A different solution that also works would be to call delayed on sum. And then that just builds up a graph, which you then get the mean. And so you can take a look at the whole operation there. Dask can handle arbitrarily complicated task graphs. This might look visually complicated, but later on we'll see some ones that are a lot crazier. So calling compute here. All right, so that took around 2 seconds. And before we took around 4 and a bit. Does anyone know why we didn't get full speed up here? We would have expected slightly more given the number of cores on this machine. Discrete, maybe? These are all being run in a thread pool. Yeah, so there's something in Python called the GIL, the Global Interpreter Lock, which means that in threads, each thread can only execute, or Python code can only execute in one thread at one time. Certain libraries, like NumPy and Pandas, often release the interpreter lock, meaning you can get true parallelism in threads, but not all operations release it, particularly most things doing with strings, and not all libraries release the interpreter lock. Not all things can. So here we got about a 2x speed up, and that's mostly because of the interpreter lock here. So in this notebook, we have used delayed to build up graphs based off of Python code. Delayed is mostly useful when you have existing code that you want to parallelize, but you don't want to change much. In the next few notebooks, we're going to talk about Dask collections that will help build up these graphs behind the scenes for you for common algorithms. Real quick, question? Yeah, so actually that is the very next thing we're going to talk about is something called Dask DataFrame, which is a Dask implementation of Pandas DataFrames. No, it has no knowledge of the functions. Delayed takes, the question is, does Dask know anything about Pandas functions? Delayed just works on Python functions and Python objects. It knows nothing about what the functions do. It doesn't know what resources they consume, anything about them. It just takes functions and arguments and builds up a graph and then runs it. Yeah, so here we have a mean value. This is just a general delayed value. It's going to be Pandas series. We'll call this is not a method, and we get another delayed value. Dask doesn't know what actually exists until runtime. At runtime, you'll get an error. Well, if there are no other questions, I'm going to hand off to Skipper.
Okay, hi. So I run the first cell just to clean things up, make things look a little prettier along the lines. So Jim just showed us how we can use Dask to kind of build up bespoke, parallelized task graphs. I never do that. I'm mostly a Dask hobbyist. I'm not a core developer or anything. But the way that I use Dask is taking advantage of what Jim said, of like these Dask collections, right? So the code that we just saw for Pandas, there was a lot of boilerplate in there. And so there's a lot of opportunities to build abstractions on top of that are like common workflows, and then to use those. So one of the questions a second ago was, does Dask know anything about Pandas? Well, kind of. It actually knows a lot about Pandas. And there's an object called Dask DataFrame, which we're going to go through here, that allows you to execute code in parallel, allows you to work with data that is too big to fit in memory, but to use the common Pandas abstractions that we're all familiar with. So Dask DataFrames are mostly like Pandas DataFrames. They're not exactly like Pandas DataFrames. We may point out a few places where they differ. And the one thing to keep in mind, like the reason that we built up some of these workflows earlier using Dask delayed is to fix ideas about how to think about things when you're working with Dask DataFrames, because it is a little different than Pandas, and we're going to point out some of the issues around that. So under the hood, a Dask DataFrame is just a like blocked collection of Pandas DataFrames. So Pandas is still doing all of the computation here. Dask is just doing the scheduling for us, doing some smart memory management, and trying to keep us so that we can do, well, for this example, computations on a single machine that maybe we wouldn't have been able to do. So there's a few links here around the Dask DataFrame documentation, if you want to peruse them as we're going through some of the exercises, and the Pandas documentation. So Jim asked who is familiar with Pandas, but not who is not familiar with Pandas. I'm curious if there's anyone in here that has never worked with Pandas before. Okay, a few people. Okay, so if there are questions of any nature, just stop me and we'll go through things. Okay, so we shouldn't need to run this, but we will. Okay, so reading in all of these CSVs, right? So we had the flights data set. It's 10 CSVs. We can look at them. So, or we'll look at the glob string. Dask provides a high-level read CSV function that works on glob strings. So we don't have to iterate through and build up the delayed read CSV objects. We can just call Dask DataFrame read CSV. DD is kind of the import convention for Dask DataFrames. So we call DD read CSV. We have we now have a Dask DataFrame object. Not too much has happened yet, and we'll talk a little bit about that. So Pandas has an operation question. Yeah.
So here, if I'm not wrong, you're loading from a wide apart.
Yep.
Do you sort? Most often doesn't matter, but it might.
Good question.
No.
No sorting.
We don't do anything that you haven't asked for. So we're very, very explicit here. So right now, this is just built up a graph behind the scenes that says, hey, load 10 CSVs into Pandas DataFrames and concap it together. If you were to call compute on DF right now, that's what would happen.
The question was, do we sort the globs behind the scenes?
Sort the globs. Sorry, I heard the data.
No, the globs.
No, we just take the result of Python.
Whatever, yeah, whatever glob.
Which is usually something on the order of the inodes on the disk.
Sure.
So that's
No lexicographical ordering. So yeah, be aware, I suppose, if you need sorted order, which you may, and we'll talk about that a little bit. Okay, so head is Pandas operation for peeking at your data. It's exposed on the Dask DataFrames as well, so we just called head on a collection of files, and we got back the first 5 rows out of the first file, however that is defined. And we can call tail. Don't panic. That was supposed to happen. So there's an error, and we're going to kind of look at what's going on under the scene, or under the hood, to understand why we got this error. So as an enthusiastic user, when I first started using Dask, I ran into all kinds of problems. And it was mainly because I didn't fully understand what was going on. And I had to change the way that I thought a little bit about doing data munging, because I was super familiar with Pandas. And things that I expected to work didn't, but it was because I hadn't properly understood what was going on. So we're going to go through a little bit what's going on here. So what happened? So read CSV. So Dask read CSV uses Pandas read CSV under the hood. Read CSV is the best and worst function in all of Python because it does everything. So Dask is just going to leverage that, but it doesn't read all of the data in. Pandas reads all the data in to infer the data types, but Dask doesn't do that. Dask doesn't want to keep everything in memory, so it just peeks at some of the data and tries to infer the data types from that. So in this case, there's a few data types that are incorrect based on the first values in the first file. And we'll look at which ones those are. There's a few ways to get around this. One is and the kind of proper, easiest way to do this is to specify, if possible, the D types ahead of time. And that's what we're going to do here to fix this. You can also tell it to peek at more data, so that there's a sample size keyword. Or you can say assume missing. So this is kind of like nullable integers in SQL. If you know that you're going to have missing data, and in Pandas and NumPy world, we have to upcast to a float, then you can say, if you think this is an integer, you're wrong, just go ahead and call it a float.
It only takes the data from the first file that it has?
First file, yeah. And then it only peeks at part of that file.
Right. When you say peeking more data, are you peeking at data, more data from that first file or data?
More data from the first file. I don't know if it would spill over to the next one if
No.
sample is bigger than the first file. No. More data from the first file.
But you could reorder the blob.
Sure. Yeah. Okay, so tail num in this case was a string. Elapsed time is a float and cancel is a bool. If we look at head up here, we can see that I think oh yeah, tail num here is all missing in the first file. So it read it in as a float. But later, it's a string. And then when you call tail, so give me back the bottom of the last file, it fails. It chokes because it thinks it's a floating point, and it's not. So we just pass in a dictionary that tells it what the types are going to be for kind of the problematic ones and let it infer for the rest. So now we can call tail, and we're in business. So one more example just to fix ideas. So what happens if we call a Python function length on the DataFrame collection, or the Dask DataFrame? Yeah, it's going to look at the glob string, figure out there's 10 files, make a set of jobs that reads in the CSV, and then calls length on each one of those, and then there's a reduce step that brings it all together. Is that somewhat clear? I think this is quite nice. A lot better than having to do this stuff by hand.
There's no shape object or shape?
There is no shape on Pandas DataFrame. So it differs from the Pandas DataFrame API a little bit. There's no shape because you would have to see all of the data to be able to get the shape. And by default, Dask doesn't know about all of the data yet. So it collects some metadata about the data frames and keeps them around. Like that's why we had to pass the D types in this case. But try to avoid reading all of the data if we can.
Is length just calling df.size.compute?
It is not. It's calling length on the data frame. I don't know if actually Pandas data frame has, if what it's doing, the dunder length is doing under the hood maybe. It's not using size.compute. We'll see that later. I think it's just, I mean, the length dunder may be doing that. Okay, so we could compute the maximum of the departure delay by using Dask delayed. So we've already seen some examples of this earlier. So we'd have to make a collection to keep up with the maxes of the intermediate results, go through, call delayed on read CSV as we saw, and then append the max of each data frame to the maxes collection, and then in the end bring it all together with the reduce step and call compute. But now we can just use Pandas syntax. So exclamation mark, because this is awesome. And this is where like Dask is Pandas aware and just knows what to do and passes things through to the intermediate results and does the reduction for us. And we have our answer. So some people had to wait 1,400 minutes for their flight to take off. And just to point out, like, we never held all of these data frames in memory at once. Dask knows what to do with the intermediates and tries to somewhat intelligently get rid of intermediate values that are being held in memory so that you can do computations that wouldn't have fit in memory otherwise. And just like with all the other delayed objects, there's a visualize method, and you can see what was going on. Read the block, read the CSV, compute the max, and then bring them all together for us. So we're going to go through a few exercises. This is also kind of a chance to familiarize yourself with some of the Pandas stuff if people haven't seen this before. We've already noted a few departures from the Pandas API and why, and often it's because we want to avoid looking at all of the data. So the parts that are missing are either impossible, not very smart, or just not there yet. Always good to ask, always good to think about. Okay, so we've seen this already, but just recall that all the calculations are lazy. You don't get anything back until you call compute, including errors, as we've already seen. Okay, so there's a set of examples here if you want to spend a few minutes to go through each one. Use head to get the first 10 rows. This is no different than pandas. Figure out how many rows in our data set. We've already seen how to do this. And then use like pandas indexing to find late and early departure times, how many there are. And then we'll also look at the canceled flights. So the question was whether properties on delayed objects are also computed lazily. And the answer is that mostly they are. So something like the size property on Pandas data frame is lazy, but the D-type property is something that is kept around on the data frame objects because it's something that we compute and keep around. So calling head should be pretty familiar to us by now. We just changed the in argument here to get 10 rows. We've seen a few ways how to do calculating how many rows there are, and there was a question about this earlier. You could either call length on the data frame, or we could use size compute, and size on data frames is a property. So this is also to your question earlier, like are properties lazily computed? By default, yeah, unless there's some reason to keep around that information. And I'll give you some time to go through the other ones. So the thing to note here is that it looks a lot like Pandas code, right? So we could still do Boolean indexing to filter the data. We could call length on it after we filter the data. So we subsetted the data frame and then called length on it. And now we know how many were negative departure delay, so how many flights left early, which apparently happens. Maybe it did in the 90s. And the late departures. One thing to note here, and then we're going to come back to later, we've already seen it, so it's worth pointing out, is that we could have shared some computation here. So we built up in the first way that I did this, we built up two separate graphs and executed them to understand the early departures and the late departures. So that means we were doing reading from disk twice. If we had called dask.compute on these task graphs, the graph would have been optimized, and we wouldn't have had to, we would have shared computation where we could. So Dask under the hood hashes the computations that it's doing so it can understand when it can share computations because it's just the same thing. So here you see I took a little different approach, used the size property, and then called compute on these results to get back the results and share computation. So how many non-canceled flights were taken, how many flights were actually taken. We can also use negation here, so more Boolean indexing. But it works just like we would expect Pandas to work. So thinking a little bit more deeply about what's going on under the hood is good, I think, to help fix ideas, help understand where problem spots are, and how to organize your thinking about your code. So one of the departures that are additions that Dask has to Pandas is this concept of divisions and the index, which is not quite the same as the Pandas index. So under the hood, Dask is, like I said, just a bunch of blocks of Pandas data frames. So in this case, we have naturally partitioned data by date. So if we have date time data, like the flights data, and it's split out for us, then we have natural candidates for a partition. So each one of these is a Pandas data frame, and the whole thing is a Dask data frame. And well, we'll see how we can set divisions to tell the Dask data frame about how the data is partitioned to speed up certain computations, right? So in Pandas, you set the index because then you get things like O1 lookup, fast operations on loc, and it's very similar with Dask. If you intelligently tell it or intelligently partition your data and then tell the Dask data frame about how you did that, then you can speed up some computations because it'll know that it doesn't have to go looking in other parts of the data for the data that you're looking for, essentially. So operations like loc, group by, merging and joining are a lot more efficient along an index than on a potentially unsorted column. So well, we'll come back to that. So let's read in our data again. Note that I didn't change the dates. I don't parse the dates here. So we have this like property called divisions, and it's just a bunch of nuns. Right now, it doesn't know anything about how the data is partitioned. It just knows that there are 10 CSVs that we've asked it to read. But we can set the index to year. And now the divisions is like filled out for us, and the Dask DataFrame knows about how the data is actually partitioned. So word of caution here, this isn't an operation that you want to call a lot. It's something that you want to call once at the kind of the beginning of your workflow, and we'll see some strategies for why this really matters later in the distributed stuff. Another thing to note here, the far right-hand bin for divisions is right inclusive. So if this weren't here, the last bin would be 98 and 99. And in this case, it's just 99. So we have 10 partitions. And now we can do things like loc, and it knows to quickly do the right thing. I only want to look in the first partition because that's where 1990 is.
Can you, sorry for interrupting, can you call .visualize on that?
On the
And add in optimize underscore graph. Equals true.
Can you make that bigger?
teachable moment. The question was, can I make this bigger? No, but I can change the format so you could write it to disk in PDF or SVG or whatever and resize it yourself. I could control plus, I suppose. Is there something that you wanted to point out here?
Oh, yeah. So if you look at the graph there, we have 10 partitions on disk. We have 10 different files. But Dask was smart enough to say that when you wanted to index out just the files from a certain year, it knows it can ignore the other 9 files. So if you actually call compute on that, it's not reading from disk all 10 files.
Right.
It's only reading one.
Right. So the takeaway here is just that it's only reading from the file that it has to, because it already knows that the data you're looking for is only in a single file. It doesn't have to look through all the other files. This is why we set the index. And you can imagine why this would be beneficial too for things like group by operations, which we'll see.
Does it support multi-indexing?
It does not support multi-indexing. That's still correct, right?
Yeah, you can have results that are multi-indexes,
Yeah.
but we don't support indexing operations as if they were multi-index. It's kind of weird.
We can talk about that later. I have thoughts about that too. But yeah, no, Dask DataFrames don't support multi-indexing right now, and this is kind of what I was hinting at earlier when I was saying that you have to change the way you think about writing Pandas code a little bit. So one strategy here might be to like set an index along like the most expensive and natural thing, and then to do nested group bys within the partitions if you need to do like a group by along multiple dimensions or something like that.
Well, sorry for interrupting. You can group by multiple columns.
Yeah.
You just can't treat the output Dask DataFrame as a multi-index.
Sure.
So when you call compute, you will get a multi-index, but Dask doesn't implement multi-indexing itself. If that makes sense.
It does. I'm not going to editorialize. Okay, so a few more exercises. Now starting to look at group by. So work through these. If you have questions, ask, and we can go through them. One thing to note here is this is the like preferred syntax for writing group bys in Dask for various reasons. So start to look at how many non-canceled flights were there taken from each airport. So try that. And then the average departure delay from each airport. And then what day of the week should you not travel in the 90s? So a few people have said that they've seen like dead kernel notifications. Yeah, some nods. Just restart them and let us know if you continue to have issues, if it becomes unworkable. Teachable moment. If you don't have like big data, don't use a big data tool. Don't give yourself another problem. Like the first rule of distributed computing is the network is unreliable, right? And things can go wrong. A lot of like what we're doing today and will be doing is like computations that you could have done with pandas alone. So if your data can fit in memory, don't give yourself another problem. RAM is also very cheap. They have really big EC2 instances now, from what I hear. Okay, so let's start to look at some of the solutions. Okay, so non-canceled flights from each airport. This should feel fairly familiar to you if you've used pandas before. So we subset the data set. We just want to look at the flights that weren't canceled. We want to group by the originating airport. And then we call either origin.count. You could use size here if size is available on the, let's see, size is available on the group by object. Oops, not my machine. Or you could pull out one of the columns and call count. How big is this? Yeah, so a lot more traffic out of Newark, at least flights that actually take off. So average departure delay from each airport. Group by the originating airport. And just like in pandas, we can index, we can use attribute lookup on the columns on a group by object. So get the departure delay. I want the mean of that and compute. We saw this before, right? So this is the exercise that we did earlier where we had to build up this by hand using the Dask delayed. Much cleaner and not a ton to think about here beyond pandas other than to call compute because we're dealing with lazy objects. And very similar solution obviously for day of week. So what was actually the worst day of week to travel? This is a test. So Friday, right? I'm sorry? Good question. It's probably Monday, right? Could be Sunday, you're right. I'm trying to think if, well, I don't know because it's not dependent on the defaults in Python. It's from the data. Let's call it, it's Monday. Sharing intermediate results. So we already saw this a little bit, and we've hinted at it a couple times. We're just going to look at it in a little more detail to fix ideas again. So say we wanted to actually look at some summary statistics of the delay, which is a good idea, and we should, because this is the worst day to travel, like there could be super high variance here. There probably is. So we can ask for the mean, and we can ask for the standard deviation of the delay for the non-canceled flights, and we can get the answer to that with 2 calls to compute. Uh-oh. They may be doing some crazy stuff next door. Oh, okay. Yeah, so we could call compute separately on the 2 results and get back the mean and standard deviation. But it's way more efficient if we put them together, allow Dask to optimize the task graph, and give us back the results this way. with a little lazy import overhead, we were able to save a considerable amount of time. So the question was about how the hashing actually works and what is being hashed. And I think you are asking too if there's a query planner. And there is no query planner. Like if you ask for the same result in two different ways, you're not going to share computation there. It's going to share computation that's easily shareable.
Does it use memorization to store the results?
For some things. We can talk about this later if you want more details.
I also have some questions about the hashing.
Yeah.
So we can talk later about that, yeah. It's very readable code. I learned a lot reading this library, actually. So we already saw this earlier, but this is just to show that the computations that can be, it's not going to show you anything. If you want to make this bigger, you can use output to PDF and look at it. But this is the sharing of the reading of the CSVs and then the computations that it can share. How are we doing on time? Is it worth finishing going through this?
I think we can keep going if you want to.
Sure.
I see some value.
Sure. Okay. All right. So this is again like how we may. Okay. So Dask doesn't do everything that Pandas can do, and what we're going to do here is look at some strategies for doing the things that we need to do using just like regular Python code or Pandas code, but still smartly dealing with our data frames and not having to hold everything in memory. So I actually don't know what CRS dep time is.
It's the scheduled departure time.
Scheduled departure time. So the scheduled departure time comes in this hourly and minute format. So when Pandas reads it in, it treats it as an integer, and we're going to turn that into a timestamp. So just to look, the departure for the first 10 flights is at 1540, right? But Pandas thinks and Dask thinks this is an integer. So we can use one way to fix this is to use time delta. So use the scheduled departure time in this format, and we add it to the departure timestamp to figure out the actual scheduled departure time in datetime format. So how we do this with Pandas? So in this case, we just take the first 10 rows. So we're actually dealing with the Pandas data frame. Head returns a Pandas data frame. Floor the number to get the hours. So we have 1540. We want 1500 for the hours. We convert that to a Pandas time delta object. So these are objects that know how to move around in time. So these are hours. Unit is hourly. Do the same thing for the minutes. And then, so we take the actual date that we have from the date parser, and then we just add the hours offset and the minutes offset, and then we get back a departure timestamp. So that's nice. So as I mentioned, Dask doesn't have everything that Pandas has, either yet or for very good reasons. And in particular, there's no toTimestamp function. So there are some primitives that Dask provides to get around these limitations. So there's map partitions, map overlap, and reduction. And here we're going to look at map partitions to figure out how we might write some code that fixes this and then apply it to all the data frames. So what does map partitions actually do? So it maps the function across all of the data frames, essentially, all of the partitions of the data frame. One thing to note here is this meta keyword. So this is another kind of departure from Pandas for very good reasons. And with the meta keyword, so Dask doesn't know what the result of this arbitrary Python code is going to be. And the meta keyword is one way to tell it. Give it like an empty container, an empty data frame with D types already predetermined so that it knows how to kind of catch the result and give you back something intelligent. Or intelligible, as the case may be. Good documentation. Okay, so we could do this in a very similar way that we just did on all the data frames. We could make a delayed object that floors the hours, gets the minutes, and then adds everything together. So again, lazy computation. So that's kind of the same thing. But now I want to have you do the same, but make it a function and then use map partitions to operate using Python code on the individual data frames. So one thing that was just pointed out that I should mention about map partitions and the various methods that take a meta keyword is that it is optional. Dask will try very hard to do the right thing. In some cases it may be slower, and in some cases it may fail because we can't plan for all eventualities. But providing a kind of a meta keyword object that like will catch arbitrary results can help you get out of some binds. Let's look. So what we did here was just take the code that we had above and wrap it in a function. The function takes a data frame, so when we map to partitions, this maps the function over all of the data frames, and in this case, takes df, computes what we want, and then returns the answer. And notice that I didn't have to pass a meta keyword here. So we could ask for this if we wanted the whole thing. So I don't think I pointed this out earlier, but head is one of the only operations that's not lazy. So I notice that I don't have to call compute on head. Any questions about Dask data frames? We'll be seeing some more. Do you want to take a little break?
Yeah.
If you want to take like a 5-minute break now, that'd be fine. We're going to have a longer break at 10:30.
We'll start back again if I see most people are here. One note before we start for the people that have seen the occasional kernel problem. It does help if you close down the previous notebooks before you start the next one, which in this case will be number 4, arrays. So wait a moment for everyone to catch up. You already saw that Dask provides primitives for basically prescribing work and then executing that work in parallel. And then the application of that to data frames, which is one of the most commonly used and useful tools in Python-based data management, data science. Some of you will use only that, but other people will rely heavily on arrays. Particularly, I don't really know the mix in the room. This is something I'd like to find out maybe later. How many people here are science as opposed to data science, which are now kind of two different things, at least in my mind? Yes? Are you? How many people here are working as science researchers? I'd say that's about half. Okay. So even if you're a scientist, you might still be working with tabular data, of course. If you're a business analyst, then you're very likely to be working with tabular data. However, arrays underpin all of that work anyway. It's good to be familiar with NumPy, which is the way of expressing arrays in Python. And lots of all the algorithms that you'll be using use the same stuff underneath. All of the machine learning, it's all really array mathematics. So arrays in Pandas actually came first, so this is slightly out of order here. And it does for NumPy what Dask DataFrames does for Pandas. And so yeah, a little visual diagram of exactly what's going on here. We're now talking about n-dimensional things, which because I have a flat screen, it's just going to be 2-dimensional here. Whereas with the data frames, you have columns, and each column has a particular type. Here we have a single homogeneous data type across all of our data, and it's split into chunks along each of the axes. So this is slightly different, and the other main difference is that the chunk sizes are known beforehand. So for the data frame, we just knew what columns there were. So we knew one of the axes completely. And we didn't know how long each of the sections was going to be beforehand. Here we do know those things, and we do know the data type, but we have splitting in all dimensions available. The point of doing this is because arrays can get very large, and you want to be able to do computations on them, either just larger than your physical memory on your machine. So this is a very common use case for arrays, is that you have maybe a laptop, maybe a somewhat more substantial machine than that, and you want to calculate through a large amount of numerical data to do whatever kind of aggregations you want to do to it, and you want to do this block by block so that you don't use up all of the memory. I'll just start with a small caveat, which is that if you're in a situation where you can load all of your data into a NumPy array in memory, then that's usually what you'll end up doing. So you could figure out your algorithms, you can figure out the workflow that you want to follow using a subset of your data, and then use this stuff to scale up to larger than memory, or perhaps into a distributed cluster setting. Okay, so again, similar to the data frame side of things, there are some things that work well and some things that don't. The things that work very well are element-wise operations, because you can do that to every single block independently, and aggregations along the various axes, and a subset of linear algebra and other algorithms that can be expressed in block-by-block terms. You don't need to know much about that typically, but perhaps it's best if I just go on to some of the examples here. If you just want to add up all of the values within a large array, then that is obviously something that works very well, parallelizable, and you don't need to keep much of the data in memory at once. So we'll look at doing that kind of thing. And as with the other examples, we'll just create some data first. So the next question for the crowd is, this data will be written to a file called random HDF5. So who has used HDF5 files or something similar? About the same number of people as use scientific arrays. It is the most common format for an n-dimensional pure numeric array. It has certain problems, and in fact this is taking rather a long time to run. So I'll just wait for that to complete. It's the creating of the data that's taking the time here. Okay, so this is the first part, was to create the data, and then a similar kind of pattern will emerge, as you've already seen. In this case, we're going to look at the data using the SciPy library. So this basically analyzes the metadata in this massive file that we just created, and we can point to the only array that we happen to have stored into there. You don't need to know the specifics of this creation function. But the point is that we have this array-like thing. This points to the array on the disk, but it hasn't loaded it, which is just the kind of thing that Dask likes to work with, so that you can then extract chunks out of it, work on those chunks, and create your results. Okay, so if we want to get a total of all of the values of the array, so a grand sum of everything, then we could do this in a blockwise fashion. This is just normal iterative Python code. There's nothing Dasky in this cell. It just says go through the range and pick out some of the data, so one chunk at a time, and do the sum of that chunk and store the sum so that when we're done, we can add up the grand total, which works fine. And the reason this works well is that the size of each of these chunks fits into memory easily, and the sums themselves is just a number, so that easily fits, and you can store as many of those as you like. From the lesson on delayed, you could imagine wrapping this in delayed very easily. We already did similar things previously. Okay, so the first exercise is just to get into this way of thinking. If you can iterate over your data and get the sum, then obviously you should be able to iterate over your data and get a mean too, which is slightly more complicated procedure. So that will be the first thing for you to do here, and I'll give you just a few minutes to do that. Since this is not yet using Dask as such, we'll do this quite quickly. All right, so I'll just display this solution, and you'll see it's very similar to the example. The sums, we add up exactly the same, and we can do the same thing, but to the lengths of each chunk, so that we can create the mean by dividing the two totals. So again, you could do this kind of thing, and you could do all of this with delayed trivially. You've now seen enough examples that you could do that, but you don't need to, which is very convenient. So you can create a thing called a Dask array using this function. For example, there are several ways to create arrays, but this is one of the most common. The input here is something that can be indexed. In this case, it's an array on disk. And the extra thing that we have to tell it is how we'd like to break that into chunks. There are some rules of thumb that you could assume here. Generally, it's nice to have chunks that you roughly have the number of chunks as number of cores if you're doing element-wise calculations. You don't want your chunks so big that an individual chunk can saturate memory, and you don't want them so small that you have hundreds of thousands of chunks, typically. But a little bit of practice will tell you what's a reasonable value to choose here. So now we have this thing called X. This is a Dask array, and just like with the Dask DataFrame, this supports many, perhaps most, of the methods that you might do to a NumPy array. So for those that have done any basic things with NumPy, none of the things that follow should seem a surprise. But the difference is, once again, when you do something like .sum, so just show, then you get back something that, again, is one of these lazy objects, a delayed-like thing. Nothing actually happens up until this point. We just get a prescription of the work that we would like to do, which is again, we could visualize this. We could inspect all the tasks that make this up if we wish to. Commonly, the thing that we want to do is actually execute the computation. So again, you can do .compute. And what this is now doing is loading in all of the chunks one by one, and it's doing sum on all of the chunks, and then it's aggregating those results together. So essentially the same thing as the loop above, but all in one step, so you don't need to worry about it, which is very convenient. So now you get to compute the mean using Dask notation. So I hope that was straightforward enough that this is trivial for you, but I'll give you a couple of minutes to think about it. In the meantime, are there any questions about how this fits together, what we're trying to do here? It's informative to just do a tab complete on the X, and you'll see that all of these methods that exist here, most of these are standard NumPy things, with a few missing, I suppose, although I can't spot any that are not here, and a few that are extra specific to Dask. So hopefully it doesn't surprise anybody that one of the ones that is there is .mean, which is what you would expect for a NumPy array, and it exists there also for a Dask array, so you can execute that, and that would give you a lazy object again, or you can then compute that, which gets you the actual answer. So the mean is 1 and a bit, and the mean up here was hopefully also, oh, I didn't actually execute it, but I'm sure that this was also 1 and a bit. Should not be a surprise given that this was the sum, and by design we already knew how many elements were here beforehand, but that's, you don't usually know everything. Okay.
Should we expect that visualize to work on result?
I think so.
2 attempts failed on my part.
In general, the visualize method is only useful for small graphs. Larger graphs, bogged down graph is, and then even sometimes your PDF renderer.
So I shouldn't do this then. I don't know. I don't know how many chunks I put in here now. I can find out. Oh, of X. So there are 1,000 pieces to this. That's quite a few blobs on the screen, I suppose. I would have thought it would cope, but maybe not on the remote machines, which are not super powerful. It's worth knowing about these helper methods that are around, or attributes. They can often tell you why things are slow, but those kinds of things come with a little bit of practice, I think. First, you want to know the basics of what works. Okay, so again, the whole point of this is that if we prescribe the computation that we want to do beforehand, which in this case is taking a lot of sums which are all independent of each other and then adding them together, or doing the mean, which is almost exactly the same thing. Dask can take this prescription when you call compute. It can schedule them on the multiple cores of your machine, or potentially on multiple machines. You'll see that shortly. And it can compute them in parallel, particularly many NumPy functions. Again, there's the issue of the GIL that you heard mentioned briefly before. Lots of NumPy operations will be friendly with that, so you'll get pretty good parallelism in many cases. Okay, so now we're going to do a slightly more involved example. This time we will, instead of creating a file on disk, which as you saw was took a long time even on here and caused one failure in the room at least that I know about. So there is, again, this is obviously not real data. So we'll make some random data that's this big, and we prescribe what chunks we would like it to have, and we can do not just a simple method on this, we can give a method with keywords so that it says in what direction that mean is taken, and we can subselect that. Okay, and Y here is, again, still a Dask array. Now, whereas we start off with a two-dimensional Dask array in this case, after we've done the mean, now we have a one-dimensional Dask array. Dask knows to interpret these chunks so that the chunk size, which was this big, now we've taken every 100th element. So now the chunk size is this big. So all these pieces of metadata propagate through nicely. The original size, so this thing, if we were to make it a NumPy array rather than a Dask array, so if we wanted to have the whole thing in memory at once, then this would be this many gigabytes. But instead what we've done is we've said, for each chunk, call the random.normal method, create the chunk, process the chunk, and then aggregate the results. So we can do this thing without choking the system. and with parallelism, which is what Dask is all about. And then we have a result. So this is a set of means in a particular direction. They hover around 10, because hopefully 10 was the input up here. Okay, so this raises the question, and I started with a caveat, which was if you can fit all your data into memory, then you're happy, right? And maybe then you don't need to worry about any of these. But unfortunately, you get more data, which is a good thing, right? More data has to mean better results. But then you have to scale out. So when NumPy starts getting slow, when your system memory starts exploding, then you know you have to move to the next level by using Dask. So this very same calculation above, which was 3 point whatever gigabytes, we could have done this using NumPy, and it would look essentially the same. But don't execute this, because it will probably crash your kernel. And it takes a while. So if you have a 16 gig laptop or whatever, then this would work, but it would still be slower. If you run it using Dask array, so again, this looks exactly the same. This is the same code as above, but has the chunks thing, and it's da.random instead of numpy.random. When you do this, not only is it faster, but the amount of memory that it uses is much smaller, because once you've used a chunk, then you can discard it. You don't need it anymore in memory. Are there any questions about this step from NumPy thinking to Dask scaling? Yes?
So one of the most common things that I end up doing is slicing or indexing an array in NumPy, just another NumPy array. So I tried to Dask, and I got the not implemented here. Do we know when that might be implemented?
It's a tricky thing to do, because it's a many-to-many problem, right? You have many partitions of the Dask array that you're wanting to use for indexing, and you have many partitions of the outer array. And you have to actually do the operation before you know how many elements you'll have in the final array. So the prescriptive method doesn't work very well for that. Is it likely to come soon? Do you know?
So NumPy has so many different ways of indexing. You can index with concrete objects. So if instead of indexing with a Dask array, you were to index with indices of a NumPy array or a list, that does work, because then Dask can reorganize that and figure out what partition each element is in and get that out. If we Boolean indexing.
Oh, if they're the same shape, then yeah. Sorry, I thought you meant the. Yeah, go on.
So Boolean indexing is interesting, because we have to know what the data is to know the output size, right? If you have a big array and all of the elements are true, then the output of your index operation is one shape. But if they're all false, it's a different shape. Since we don't know what the values are, we can't embed that in the graph, knowing what the output size will be, if that makes sense. But you can use Dask to implement the where function from NumPy. Second? Mask also works, yeah. Where and mask work, yes.
Okay, there are a couple of questions here for open discussion, and again, I ask you not to actually execute these. That's why the code is not in a cell. So here we had a speed up from 20 seconds to 4 on whatever machine was used to do this timing. I didn't rerun it here. And the chunks that we gave here for something of the size 20,000 by 20,000 was 1,000 by 1,000. And the first question is, what happens if we give this as the chunks? I didn't specifically tell you, but this chunks parameter tells you the size of each part of your Dask array. So that is the size of one of the NumPy arrays that are constituent. So what happens if we put in chunks here, 20,000, 20,000? Any thoughts? First of all, oh, go on.
It will try to load the entire thing. It will just have one worker, right? Because the entire thing is one chunk.
So you will indeed have one chunk only, because the chunk size matches the overall size. So the one constituent NumPy array constitutes all of the data. And yes, exactly, the scheduling of that would mean that one worker works on it. So if you have the memory to do it, it will still work. But you will go at the speed of the original NumPy implementation. So it will either go slower because there's always some overhead to managing Dask flow of data. You basically don't do it. It doesn't make sense. Okay, and the second question is, what happens if the chunk is this much smaller number, 25 by 25? Any thoughts on that one? Right, so the question is, how many chunks would you have in this case? And the answer is a lot. I'm not going to do the calculation. But that means that this y thing, which is the lazy object that contains the description of the calculation to be performed, will be massive, because it will include, for each of these many, many, many chunks, do the mean, do the mean, do the mean, all the way through. And that's just a massive piece of memory. That's one problem. So it could be that the prescription of the calculation itself is big enough to trouble your system memory. The scheduler has to deal with this, so it has to take them one by one and farm them out to workers, which are threads here. Each element of work executes very quickly. So in a case like this, where 25 by 25 mean happens in I don't know, microseconds or something, the time it takes to manage the data between the workers, allot the work, and all that kind of stuff will easily dominate, and you'll end up running much, much slower than either the original NumPy one up here, or even slower than the more optimal version here. So if your chunks are 1,000 by 1,000, you have a million elements here. These are floats, so that's like 8 bytes per. So having pieces of memory that are many megabytes, let's say, is a reasonable rule of thumb. You definitely don't want to be below the megabyte threshold, and you don't want to be up where each chunk takes up a noticeable fraction of your system memory. So obviously then it depends on your system what will work well, but somewhere in that regime is where things will tend to be most efficient. Yes?
So that example, the fast example with Dask above, that is faster than the NumPy example because Dask is running the computation in those workloads, right?
Mm-hmm.
Is there a way that
Also memory. So if you approach the memory limit of your system, then things can slow down by a huge amount.
So if, if you were doing something that doesn't release the bill, like some big Python computation or something like that, then you wouldn't be able to parallelize the thread.
Right.
Is there a way to tell Dask to do like multiprocessing?
Yes, and we'll be getting to that. Yeah. Okay, another preparation step. I'll set this running before I tell you about it. So we've included a small amount of weather data that's in the repos that you all have access to. And this task takes it and interpolates between it to make it into a much bigger data set. So it now looks like a real scientific data set. Obviously, it would be nice to distribute actual massive data to everyone, but that would involve sucking it from some third-party storage that we didn't want to implement. So this is a similar kind of procedure as you might actually do. In this case, the weather is its temperature, surface temperatures at time steps. So it's a multidimensional, but again, there's a single type of value at every measurement. And this gets stored, in this case, into a set of HDF5 files. Again, HDF It's very common in multiple branches of numerical computing. I don't know how many people are here from different branches of science. I used to be in astronomy. We only dealt with FITS files. I don't know if anybody is afflicted by this. I also worked in medical imaging, so I also dealt with DICOM, and there are dozens of different formats that do essentially the same thing. They all have problems, including HDF5. There is an HDF5, the next generation talk, I think it was on Thursday, that maybe says that most of those problems are solved, so I won't go into them just in case I don't need to. Okay, anyway, so there are now, once you've executed this, a bunch of these HDF files in a weatherbig directory, and we can tell H5Py to open them, and HDF5 itself is, again, also lazy by default, so this just says, well, there is a dataset on disk, it's this big, and it's this type, which is just the kind of thing that Dask wants to work with. So before invoking Dask on it, you can just get some part of this data. And indeed, if we wanted to load one of these data sets, we want to load it, subsample it, and display it, then this will do that just fine. This is, again, without Dask. But it takes a while. So again, the data is, so this is for one of the data sets. The data is already quite big, and it takes a certain amount of effort on Python's part to process this, and there is your image, where you can make out the continents on here. It was, hot in Texas, cold in Toronto, because that's where I live. So, okay, anyway. We will have a task now for you. So I will set the task and then take you through it. So this is a bit of a pipeline here. The solution is below, so we'll come to that when we need to. So there was a list of H5Py objects. These dsets is a list of objects. So can we make from this data set, using the from array function, a list of Dask arrays? So from array takes one of these H5Py objects. You need to tell it the chunks, and it gives you back an array. It may be informative always to look at the documentation, and there are some examples in here, including an H5Py, right? This is very similar to the lines that are above. So I'll just give you a couple of minutes to think about that. So the example demonstrates for you that to load one of these dsets, as we call them, which is the list, if you wanted to load one of them, then you would do something like that. This is the chunk size that we're told to use. So again, this doesn't load it. This just sets up the prescription to load it. If you wanted then a set of these, then probably the simplest thing to do is a list comprehension here. For example, like that. Obviously, there are alternatives here, but that's pretty straightforward. And then the second part is to investigate the next Dask array function, which is stack. So if I execute this and look at one of the things that I've made, it's a Dask array with a shape like this. And we would like to, and also there are (31) of them. So we would like to stack these 31 arrays so that we get one uber array that is now of the shape like this. So again, the stack comes with, da.stack comes with documentation. You can have a look at how to do that. And then the final part will be to take the mean and plot it. Okay, so now there are a few steps to think about, so I'll give you a few minutes to work with that. And in the meantime, again, any questions or discussion, it's good to keep the room alive. Okay, in the interest of time, I'll take you through the solution. And the last couple of examples here we'll skip and you can have a look at in your own time. So this is repeating some of the code from above so that you can see everything together. Get the files, open them as HDF datasets, and then create arrays from each of them. This was as far as I'd taken you before. So again, from array, you just pass this thing. Sorry. You pass the chunks size in that you want. And then the new function was stack. And the only thing that you really needed to do here was decide which axis you wanted the 31 elements to be oriented along. This remembers the chunk size and the shape of the arrays you gave it in, so you get this aggregate shape that we're after. And then if you want the mean along the 0th axis, then you do dot mean along the 0th axis. I should show this running for you. And then there was a second task that maybe some people got to, which was to compare day 0 to the mean. So selection like this works. And this will take a few seconds to complete. And then we'll stop the array section here. It is interesting. Yes?
Don't you have to call compute?
I'm just wondering about that too, but it seems to be doing it itself.
So Dask arrays implement the array protocol, which means that most things that happen in array lengths, so matplotlib, for example, will automatically call compute and just give array.
Actually, yeah, matplotlib does an as array or something, right?
Yeah, that's exactly it.
Mhm. Okay, it's done one. Okay. And then the second one is still working. So I'll hand over while this is finishing. Oh, okay, there we go. So this is one particular day compared to the average. And again, obviously it's called in Toronto because I can just about see where the lakes are on there. Okay. Any last questions before the end of the array part? No? Okay.
So I lied accidentally. We're not going to take a break right now. I'm going to go through the bag stuff fairly quickly just to introduce it, make sure you're familiar with it, and know the kind of last big collection in Dask. Then we'll have a break, and then we're going to switch over to talk about the scheduler and some of the distributed stuff, which is super fun. So I should shut this down, yeah. So this is how you shut down the kernels that we mentioned earlier, or could save you some headaches. Oops. Okay, so bag, like I said, is the last kind of big collection in Dask. Bag is parallel lists for semi-structured data. So what does that mean? It's kind of a multi-set. It's a collection of Python objects. So if you have like JSON data or deeply nested data or like basically just really messy data, you may want to use Dask bag to clean the data before you bring it into a either different or more performant data structure, like a DataFrame. So we're going to look like whirlwind tour through some of the primitives, what Dask bag can do for you, and what more to the point it can't, and maybe something that you should prefer DataFrames for, or something like that. So is anybody here work with Spark? No? Okay. That's fine. And probably good. So the Dask bag is built around functional programming primitives. So operations like map, filter, things provided by the tools library, and then like does parallel execution, obviously. Again, here's the links to the documentation and the full bag API. But let's just get a flavor for some of these things. So go ahead and run the first cell to create the data. Is done, and we'll use that later. So first is creation. How do we create a bag? You could create it from a sequence. You probably aren't going to use this very much, but it's good for like quick getting started and fixing ideas. So again, lazy. There is facilities for reading text, so reading arbitrary text. So what we did above here was write a bunch of files that has some accounts data that we'll talk a little bit about, like what's actually in it. But it's a JSON object per line in a file. And so Dask doesn't know anything about that. It just knows that it's a file with new lines, I suppose. And so read text is a way to create a bag based on any kind of text data on disk, whatever it is. So we have 20 files. The bag has 20 partitions, so it'll read in a file if we ask it to. And like all of the other Dask objects we've seen, there is a visualize method. Where is this data? So yeah, we have 20 files that are gzipped to JSON. So it's not only text, it's compressed. So I already mentioned the bag is like built around more functional API, which some people may like. It's a little different than working with like Pandas data frames and a little higher level abstractions. But just to get an idea, so we can call filter on a bag. So we create a bag from a sequence and then call filter on it like we would in Python. So only give me back the even numbers. At this point, no computation is actually done. And then we're going to take the even numbers and then we're going to square them. So we can call map again on the object that's returned. So nothing has happened yet until we call compute. And then it blocks until it's done. And we have squares of all of the evens. So the data that we just created, it's similar. So who is not like a practicing scientist? I like to ask the compliment. No one. Anyone like from industry or a couple people? Okay, sure. So if you work with data from like a document store or transactional data, anything that's like highly nested and messy, I wish I had very clean heterogeneously or homogeneously typed data on disk to work with. That sounds lovely. But if you have messy data, nested data, transactional data, if you deal with Twitter data, stuff like that, text, bag can be pretty handy. So in this case, each line is a JSON object that has an ID that you can think of as a unique identifier for like a particular customer. the name of the customer, and then a list of transactions. And within those transactions, so the transactions is the key, are transaction ID amount pairs. So we can actually take a look at this. So read text, you can use globs, and then take is kind of like head for data frames. We can look at the first object. And in this case, so we didn't tell Dask bag anything about the data, so what it returned was just the first line from the file. So you can see this is a string, and there's still the new line at the end here. So we have the ID for this customer, the customer's name, and then the key, transactions key, which is a list of, again, JSON objects with amount and a transaction ID. Though decompression did happen automatically, we should note that. So to turn it into something useful, we use map and we use JSON loads. There's a faster JSON loads that you may want to use if you're really trying to optimize things in Python, but the standard library will work here. So now we have dictionaries that we can work with, so standard kind of Python objects. So let's look quickly at just kind of a basic query again to get a flavor, and then we'll talk about some of the higher level abstractions, I think. So now that we have, notice that I caught the result from mapping JSON loads onto the file, or onto the collection of files here. And now, so it's again lazily computed, but this is the thing that we probably want to be working with. So I kind of threw away the original lines bag, and now we're going to work with JS because we want to work with the dictionaries. So we can call filter on that. We can pass arbitrary anonymous functions using Lambda to filter. So if we only wanted to get Alice, we could filter and then say, give me the first 5 just to look at and fix ideas. So now we have the 5 first elements where Alice was the name. And if we wanted to go in and kind of unnest that a little bit and count the transactions in each of these records, we could filter down to Alice and then use map to map a Python function over the result of this. In this case, count transactions. We're getting back those dictionaries. So we want to keep the name, and then we want to just ask for the length of the transactions key, or the value. And then look at the first 5. So pretty nice way to go from like pretty messy data down to something that we actually want to work with. One thing to note is that there's a pluck method. So pluck method is kind of like get item right within the nested pairs. It's one way to pull out the results, intermediate results, or keys from the dictionaries. So here we're going to map the count transactions like we did here, and then we're going to pluck. We just want to pull out the count. So we could have just only returned the count, but pluck is a way to get around that. So in this case, now we get back a tuple that has just the values from the key that we asked for. I'm going to skip the examples for now. Just want to give you a flavor of this. Flatten, another method of interest, like to de-nest the data if you have to deal with highly nested data. Two higher level abstractions, I guess, on the bag are group by and fold by. Group by should be fairly familiar to you from the Pandas stuff earlier. The one thing to note here with group by and fold by is that group by is not very performant on bags, and you may want to use, you almost certainly want to use fold by instead, or you want what you're really after when you're working with bags is I have all this dirty data, I want to clean it up, and then I want to put it into like another data structure. Like I want to put it into tabular format, I want to clean things up, throw away stuff I don't need, keep what I do need, de-nest the data, and then use something like a DataFrame. So if I was going to do group by, I would clean the data, put it into a DataFrame, and run group by rather than doing it in Dask with the bag.
The group by is like, you said like pandas group by, not like linear tools group by.
What's the distinction?
Since pandas has an index associated with it, it'll collapse down and then return as an index, whereas the inner tools will, if you say group by and you give it some key, every time it finds that key, it breaks it into a chunk,
Sure.
and then it'll return all the chunks. It's a slightly different operation.
So Panda supports
Basically,
both,
you
right?
sort the list first and use the inner, and then use the inner tool to get the same thing back.
Sure.
Otherwise, it doesn't. And these groups will
This
just-
is like pandas group by.
It's like pandas.
Yeah. And the reason it's not performant is for group by, you have to do a full shuffle, because you don't know what partition each of the keys are in. Where fold by, you add in a merging function, and then you don't have to do a full shuffle, so you can actually get parallelized results. So think like fold by is more like group by with a reduction at the end.
Yeah. It looks very similar to the array example that we just saw earlier. So yeah, I think I'll leave you with that. Like if you're working with bags, like consider using fold by. I don't think we need to get into the details of fold by here, especially if we don't have too many Spark people. So the reason I'm kind of going through this fast too is bag's a very particular data structure, and it's not super heavily used. It's great. It's a great tool if like it solves the problem that you have, but if it doesn't, like it's not often something that you reach for. Yeah, the example here like just illustrates a common workflow that you might want to work through, like I've already said, going from this dirty nested data to like a flattened array structure, a tabular structure, sorry, and then working with the Pandas data frame. Yeah. Any questions about that? I know that was a whirlwind. Just want you to be familiar with it, but yeah, there was a.
I have a question.
Sure.
For the data frames, actually, since I ran into this problem recently, is there any way to, if you have your data frames basically pre-checked, let's say you have a whole bunch of CSV files and you say, okay, read in this, all of the files that follow this regex, is there any way to access for each of the partitions the name of the actual file that it was read from?
That's a good question. Probably, right?
No.
No.
You can manually do that. So you can dip over your files yourself, build a frame, and then concatenate it together in Dask to the right thing. But we don't catch the file name.
Oh, yeah.
We just use Dask to read CSV.
Yeah, that's what I ended up doing.
Yeah.
Yeah, there are tools
It's
for
not part of it,
your,
correct.
making your data frames or any of these collections from delayed. And in delayed, you can arbitrarily put whatever kind of function that you want. So you could include it like that.
That's what I did, but I was wondering if there was something built in that would make this necessary.
So the question was whether when you're using read CSV on a glob, if you can figure out the actual file name after the fact for the partition, and the answer was no, not very easily.
The data frame structure has a name argument, and you have to read the CSV to assign that.
You could. We don't do that.
But I mean, is that an option in the read CSV where you can assign the name as the data?
If Pandas does that, they could do that, but we don't implement that extra. So I don't know if that's an option in Pandas. If it is, I don't know that.
Yeah, that sounds
Well, you
That's
could do a map partition, right?
new to
You
me.
have to know what the partitions are, which is the same as you got before.
No, you do
Anyway.
map partitions, and for each partition, it's the F name. Is it there?
But it's not in the.
I've never seen this before.
Okay. I thought you were saying it was just
Okay, do we want to take a break? Yeah. So now you can have the break I promised 15 minutes ago.
All right, well, in the interest of time, I think we're just going to get started, and people can trickle in as they do. So make sure you close out of your previous notebooks, just so we're not using up resources on our small remote system, and open up Notebook 6, Schedulers. So far we've been talking about building different Dask graphs, building task graphs using delayed, Dask array, DataFrame, bag, different ways of actually prescribing what computations need to be done. But these need to be run somewhere. So Dask has multiple different schedulers so that these can be run upon. And each collection has their own default backend scheduler. So array, DataFrame, and delayed usually run in a thread pool, while bag runs by default in multiple processes. This has to do with the global interpreter lock that we mentioned before. Most array and DataFrame computations do release the interpreter lock, and so you can get true parallelism in a thread pool, while bag is more for general Python objects which do not release the interpreter lock, and to get actual parallelism you need to be running in multiple processes. Walking down through here. Quick run these two. So to specify schedulers, we have a couple different ways. You can specify schedulers by passing in the get keyword to the compute method. So here, right here, we're specifying to use the multiprocessing scheduler. Or you can pass it into dask.compute, so the compute function also takes the get keyword. The other way of doing this is you can use set options. Dask.set options as a context manager. We use for specifying a couple parameters that usually the defaults work fine, but sometimes you want to tweak yourself. So one of these is specifying the scheduler. So you can say, I want to use the multiprocessing scheduler, and it'll be used completely within the context manager. So all code under this block will use multiprocessing. Or you can set it once globally by just calling it at a top level. So just to demonstrate, here we're walking through the previous example we had using the flights data. And if we call compute by default, it will use threads. And that takes, I don't know, a handful of seconds if I remember right. Yeah. I'm not going to run this cell. This takes a very long time. Something we're trying to, wait for people to walk in, message lately. The multiprocessing scheduler has some flaws that are unfixable with its current design. It works great for bag. And things that are mostly following the map-reduce type paradigm or are not serializing large intermediates between it. But for things like data frames, where you might be wanting to send some data between one process and another, it has a flaw in that the multiprocessing scheduler pulls all intermediates back to the main process before sending them out. It says, hey, workers, do a bunch of stuff, gets the data back, and then sends it out again to the workers. It doesn't leave it where it is. This is fixed with the distributed scheduler, which I'm going to talk about in a second. The distributed scheduler is kind of a misnomer because it runs perfectly fine locally, and you can use multiple processes to get actual true parallelism. That it fixes all the issues with the current multiprocessing scheduler. But for things like Dask bag or simple map-reduce type patterns, multiprocessing works fine. The third single machine scheduler is just dask.get is aliases. It's a single thread, runs in the main thread. It's mostly useful for profiling and debugging. Often if you want to be debugging something, you want to be dropping into PDB. Running in a single thread for that works fine. It also works fine with the threaded scheduler. PDB does play well with Dask. So I'm going to be moving through this fairly quickly because we have about an hour left to cover some stuff. By default, the schedulers will use as many cores as you have on your box. This is lying. We have allocated this all with Kubernetes. Figuring out how many CPUs are actually on the machine is what this has done, rather than the small bit that I'm allocated. But by default, Dask would try to use 64 CPUs. You can set that manually by passing in the num workers keyword. And again, that's a setting just like the scheduler that can be set globally or locally. Skipping that. We have many different ways of profiling and debugging. I'm giving a whole talk on that on Thursday. I'm not going to talk about it now. But these notebooks are all runnable locally as well if you wanted to download afterwards. I was told to mention this. The slides have the link right here. And I'll leave that up at the end of the talk. So people wanted to get that. So all the stuff that we're breezing through, if you wanted to take a closer look later, you can. All right, so the distributed schedule that I mentioned. So we had the three local schedulers. The threaded one runs in a thread pool, multiprocessing runs in a process pool, and the serial one that runs in a single main thread, which is good for debugging and profiling. The distributed scheduler is a separate library. It can be set up on multiple nodes. You can have multiple different computers across a whole system computing with Dask, or you can just set it up locally. So to set it up locally, we'll do that first. You just import from dask.distributed, import client. Client is the access point to the distributed API, and you just create one, and that's it. So it's doing that here. From Dask distributed, import client, and we create one. It'll take a couple seconds just as everything spins up. By default, calling client with no arguments creates a cluster with one worker for every core. I'm wondering if it's going to be doing that. We switched how we were setting these up. Yeah, okay. If you haven't run that cell, do not run that cell. Let's quick fix that. Maybe I'll just run this locally from distributed import. All right, cool. This is just for demonstration purposes. We actually have a system set up across a whole cluster for you that is set up properly. But locally, if you're running on your own laptop where we weren't getting CPU count lying to you with what you've been allocated, just calling client is normally how you'd do this. So then by default, when you create a client, it takes over as the default global scheduler. So if we were to run our previous cell with the largest delay, which is a Dask DataFrame. Oh, since everything died, I got to redo that. Cool. If we call compute here, this is going to call run on the distributed scheduler by default now.
Is there a way to it's working on getting a connection there?
Are you running the cell as it was? Okay, yeah. Yeah, so the issue is we use multiprocessing.cpu count to figure out how many cores you should spin up by default, how many different workers. This is running on a distributed system where lots of you are sharing the same actual hardware. Oh, you have it as I have right there?
Yeah.
And you're getting a connection error?
Yes.
You might need to, I'm not sure. Things should just work. Maybe restart your notebook and try again.
Probably too many going at the same
Yeah, it also might be trying to allocate too many things on the same single node. This is just for a quick demonstration that things work locally. We're going to be using the actual distributed scheduler in a second here. So it takes over by default. To run on a distributed one, you just need to have system set up. We have many different tools for doing that on common systems. So there's a command line called Dask EC2 for spinning up a cluster automatically on EC2. We have ones for Kubernetes, Marathon, Yarn, various different systems. Usually there's some nice utilities for making these work. I'm going to quick demonstrate how to do it locally if you wanted to see that. So you don't need to set it up this way, but a command line, it's just three things. So you have a Dask scheduler command. You just hit enter, and that's going to spin up a scheduler. And one of the things it's going to print out is the scheduler's address. And you just need that. And then in a different machine, this is just a different tab on my local laptop, but a different machine, you call Dask worker. And that will spin up, by default, a single worker process with the number of threads as you have cores on that box. And these are all configurable. You can specify how many processes you want, how many threads you want. And then if you run that on all your different nodes, you can then connect. And in a third one, I'm going to import a client. And then just a client, you pass in the scheduler address. And you can see that I have a single process with 8 cores. So we've already set these up for you. Each of you should have your own distributed cluster running at this address right here. If I just run that, I can see that I have 8 workers with 32 cores and 48 gigabytes of memory across my whole cluster. So now we'll try running our Dask computation from before. We have the graph building up off the data frames, which should, the new client took over by default, so this should run fine distributed. And we get a big error. So one of the things you need to think about when you're moving from computing on a local node to computing distributed is file systems. So you're running in multiple workers, and they have different environments than your single local setup. So right here, all of my files that I was trying to compute on exist on my normal, on the head node, where my notebook is running, but they don't exist where I'm actually running those computations, which is the worker nodes. So often you might use some kind of distributed file system. You could use HDFS. You could store things on S3. You could duplicate everything. You could move your files so that they exist on every node. There's lots of different ways to get around this. For now, we're just going to make some fake data. You don't need to understand this cell at all. This is making a data frame that looks like it, but is all fake data. Create the same computation as before, and we can run it. And this is going to be running distributed across all of my workers, ran at about a second. One cool thing about the distributed scheduler is we have an awesome diagnostics page. There's a link right here. This is going to open up. This is a Bokeh application. Bokeh is a cool plotting library. You all should use it if you want. It makes awesome distributed plots, but it's really useful, we found, for plotting streaming data. So as things update, we can make nice charts to figure out how things are working. So I'm going to run that same computation as before, and actually, just so I can talk about it, I'm going to run the loop. We'll run it, I don't know, 10 times. Cool. So while that's computing, we can go over here. This plot right here, each of these rows is a single worker. Let's see. There we go. Each of these rows is a single worker. Each rectangle is a task. And if you hover over them, you can see the actual title of the task. So here, this is building up my imaginary data frame. If we zoom in a bit, I can see this is taking the max of a series. Red is data transfer. So red is serialization between one worker and another. Data that lived on one worker might be needing to move to a different worker. So there's all sorts of different tasks. Down below, we don't have anything running right now, but if I was to run that again, we've been getting this with, over the network, for some reason, the plots aren't updating as well as they do over better Wi-Fi. You can see, here's progress bars for every task that's running. So you can see the different read CSV calls as they progress through. Up top left, let's run that again so we can talk some more. You can see bytes stored on each worker. So every row here is a worker. Bars signifying bytes. They'll turn orange as workers get filled up, and then eventually red when they start spilling to disk. Dask will automatically spill to disk once you get enough memory in a single worker. It'll start writing intermediate values it's storing to disk so it doesn't memory overflow. One caveat with this is that's all based on its estimates of the intermediate values. So Dask knows approximately how much, or like how to figure out the memory size of a NumPy array and Pandas DataFrame, but not everything. And so we're estimating how much memory is held by every intermediate value to figure out what we're actually going to spill to disk. Yes? On the worker node. Say again? Which directory does it use? That's a good question that I'm not able to answer. So
You can specify
You can specify it's configurable. Okay. Cool. Did I have anything else? We had some exercises running those. We are going to skip them to move on to more interesting things. Any questions real quick about setting schedulers and the different schedulers? Yep.
Can you access, so right now you're accessing a pool of CPUs, can you access GPUs?
So the question is, can you use GPUs? Dask itself has no concept of GPUs, but one thing you can do is when you're spinning up your workers, you can specify capabilities. So you can say this worker has a GPU, and then later when you're saying where to run things, you can say run this computation only on workers that have GPUs. Dask doesn't know the term GPU, but Dask knows the string GPU that you can say it's a capability of that worker. If that makes sense.
How do you get the link to this diagnostics page if you spin up your own local cluster?
So by default, it's always on the same port. But if we go back to scheduler info, you can see after the scheduler address, you have the bokeh address, HTTP. You can see actually here's the local directory that it's going to be writing to. It's just a temp folder, but you can configure that. So yeah, by default, I believe it's always on port 8787 of the same TCP as the scheduler. So shutting down the notebook 6 and moving on to 7. Martin, did you want to take this?
Yeah, okay.
Okay. So we're going to be moving on to talking about distributed data frames. So computing using distributed on a collection of this type.
Which will seem very familiar, hopefully. It's a combination of the data frame concept where you break up your data, but now we're also splitting it across machines. That's all fine. We just need a worker on each of those machines that can take instructions from the scheduler, which is exactly what we have set up for you, and in general is not difficult to set up in a whole different wide variety of possible cluster architectures. Okay, so there was this problem of what files do you have on what machines, and this is a general problem when you talk about multiple machines. You could have a file system that they can all see, or in this case, they could have a remote data storage that they can all have access to. This is very typical for, say, the Amazon or Google setups. You put all of your data in some kind of long-term storage. This particular one will use the Google Cloud Storage Service. Dask can interface with that. It can interface with S3. It can interface with HDFS and potentially some others. Azure, I think, works more or less for anybody that knows about those things. But the point of it is that when you do read CSV, the thing that goes in here doesn't have to be local files because, again, you would have to make sure that those local files exist for all of your machines. So what this is doing instead, it's talking to Google Storage, and it's asking for a list of files that matches this, and it will run this through Pandas read CSV, where each of the Pandas read CSV sees one of the files, or some part of each of the files. And these are the typical things that you saw previously. So now instead of fake airline data or just an extract, we have this real data set that exists on a remote data storage, and we can treat it in exactly the same way as before. Except when we call head, of course, it now has to actually talk to Google and fetch the first chunk. So because network communication is always going to be much slower than disk communication, expect startup times when you initially ingest data to take longer. But it's the same thing as previously. One important thing that the distributed scheduler gives you is finer control over what is in memory, because the whole point of this is that whereas previously you're worried, oh, I might fill up my 8 to 16 or whatever laptop memory you have, Now you have a whole load of machines, and you can store data in memory on those machines because inputting data is typically slow. Cleaning data might be slow, but you want the queries that you run on the canonical version, on the final clean thing, you want those to be fast. If you store things in memory, then Pandas is a very highly optimized thing. So for a Pandas data frame, most operations on it run very quickly. So if I can split my data into Pandas data frames and store it on a number of machines, then my queries can be much, much faster. The key thing to look for is .persist in this, and that will take the prescription of the data frame that you've built up so far, load it into memory, and then whereas before x was the prescription, now instead x is a pointer to all of the pieces of data frames that exist on your cluster. You can, just like with compute, you can also do multiple ones at the same time, which is convenient. Okay, so we defined df up here to point to this remote data. And we want to persist it. So I'll just do this for you, since it was really given to you above. If you run persist on this, then again, df up until now is the prescription. With any other, if you've done some addition of columns via maps or selections or whatever, that's all part of that prescription. Now we turn it into a materialized in-memory thing that's distributed across our cluster. And if we go across here, then you'll see some things start appearing in memory. Progress again is down here at the bottom. So you can see that the time to read is relatively slow. But once things are in memory, processing those into data frames is fast. And, sorry, this was the reading one, the one that's ahead. Once it's in memory, processing those things will tend to run much faster. Okay, so this ends, and unlike the previous one where this cleared out after we were done with our operations, now we have this bottom row, which is the from delayed, which is the interpret this as a data frame. 85 complete and 85 in memory. And those things show up here. So the total memory usage in our cluster is 18 gigabytes. What's the total amount available? What's the total amount available on this cluster?
32, I believe.
Okay. Now we didn't do, I don't remember how long this took previously on a single machine, but now everything is in memory. These are again optimized Pandas operations. So when we run this, it was too fast for me. You can see on the plot, all of these are the little Pandas operations. They're fast because everything is in memory again. And here is your result, where the vast majority of the time now, it might be actual Pandas computations if it's something complicated, but now you have to, because you're on a distributed system, communicate between the different workers, so that can be also significant sometimes. Okay, it's important to realize again, and we said this before, that the Dask data frame is actually a collection of Pandas data frames, so you can operate on them using your usual Pandas methods, and you do expect them to be fast. Again, it's always good to profile everything that you intend to do. And you can get some information about your data frame so that you can try and make rules of thumb of what's likely to work well. On the index, if your divisions are known, then things that involve using the index, so joins and the like, will be much faster. Unless you've put some effort into knowing what the index is, you will not in general know that. So in CSVs, they're just files. You don't know until you've analyzed each one what values you have in different parts. But you can always set an index if you want to, which doing that at the right time for the column that's going to be most important when you do your queries will really accelerate your work very much. Okay. I will have you do this one, I think, because this is nice and quick. I already told you that here we know what the total is of the bytes in memory. This is a useful thing to keep an eye on. But you could want to do this for yourself, commonly as a precursor to running the whole big query that you might do later. So we have this thing, df, and df has a method, map partitions, which will take a function and apply it to each of the sub-data frames. The thing that we're interested in is using this pandas function to figure out what the total memory usage of all of the pieces is. So again, this is the stuff. This is, we can do this because the pandas data frames, the constituent pieces are now in memory. If they weren't in memory, then to find out how much memory they take, we would have to load it and then measure it, and that would be a fairly lossy thing to do. So some things go in here, and then you might want to do something with the output. I will give you a few minutes at doing that. While you work on that, I will mention that although the status tab here is the most important one and the one that you typically keep an eye on, there are other things in here that are worth looking at. So workers will tell you the state of your various workers, their individual memory use, for example. Tasks is a longer look back on all of the work that you've run since the cluster started up, and so on. So I'll leave that for you to check on. You can apply arbitrary functions to the parts of your data frame. So the memory usage does this. It actually tells you the memory usage of each of the columns, which is why we're told that we might want to use sum here. So if you use .sum, if you apply sum onto each of these, which you could do as a single function that does memory usage .sum, or you could apply it again if you want to. Would that be just sum? There are many ways that you could choose to set these things up. This tells you then the memory usage of each of the partitions, of which there are 84, apparently. So if you wanted the grand total, then you could do a sum before or after the compute, and it wouldn't make a whole lot of difference in this case. Yeah. Which is, I don't know, quite a big number. But the idea is here that you are now farming out functions that operate on these data frames across your cluster. And so if you understand pandas, then in general, although not all pandas functionality works, you can always get to where you want to go with a little bit of practice. So I will just mention that in the rest of this notebook, there is some information about the index that I already mentioned, and you heard earlier too. So this is going to be important depending on the types of data analysis that you want to do. It's a very common step after cleaning, but before your major queries. So I'll just leave you by saying that the index is important, and you should carefully consider the nature of your data, before you turn to doing your queries. Again, if profiling suggests that it may be necessary. The particularly interesting index that you might choose, this is very common, particularly amongst business-oriented people, is time series. So you have some quantity or quantities that is regularly sampled. Then natural things that you might want to find out is what's a monthly rolling mean or something like that. And if you set your index to be a time series, so timestamps, then the normal pandas functions that deal with those timestamps, such as resample in this case, resample.mean, this will give you the mean every month, 1m for month, I assume, rather than minute. I always forget those. Then these will just work for you. And so that's a great convenience for many people. So that's all on distributed data frames. They work like normal data frames, but remember, persist. It will save you a lot of time in the right situation.
You leave that up, actually?
Yep.
All right, we're going to try to quickly go through one final notebook, and then we'll have time for questions at the end. So if we look back at the status bar, though, this is just what I wanted to show. I still have all this data in memory. That will be kept around as long as Python still has the reference to the data frame that the Dask data frame that data is from. If I close this notebook and then shut it down, the scheduler is still running. But you can see the data all went away because the Python cleaned it up, and so then Dask garbage collected the data that was working on the scheduler. Dask schedulers are actually multi-tenant. You can have multiple people working on the same cluster, sharing the same resources, and Dask will figure out how to work that all out. Also, one cool thing, since we mentioned the hashing earlier, is if you and your friend are sharing the same cluster and you both try to compute the same thing, Dask will only do it once and send you both different results. So, anyway. So moving on, the final notebook we're going to talk about is some advanced things to do with distributed. So the distributed scheduler is like any other Dask scheduler, but it also has some additional API methods that you can use to do slightly more complicated things, depending on if that fits it. So one thing is, we'll just quick recreate our client. This is still connected to the same scheduler. How many people have used concurrent futures before? Okay, only a handful. So Python has this standard library feature, concurrent.futures, which is a way of doing asynchronous computation across thread pools or process pools. The distributed scheduler has an almost drop-in replacement for that, but running across a cluster. There's a separate thing we're not going to talk about, which actually wraps that and then does make it a drop-in, but we changed some things by default to make it a little more performant on distributed. So just to dive right in, we'll define some simple functions again. Inc, dec, and add. Same as before in the delayed notebook, adding in some sleep to make things slower. So the first function we're going to talk about, first method, is submit. Submit is like apply, if you've ever used apply from Python 2 or got rid of in Python 3. It takes a function, so any callable, and then arguments and keyword arguments, and then it will run them on the cluster. So I'm going to run that. And over here we can see it's processed. So right now there's one task processing, and then it finished. What it returned was not the actual result, though. It returned a future object. Futures have a status, so right then when it repered, the status was pending, and then it has the key in the graph. If we were to look at it again, we can see the status is now finished. That computation is done. If you want to block, so let's run that again. This is still running because it's sleeping for a bit. If I call wait on it, it's going to, it's the same computation. Hang on. If you call wait on it, that cell will block, or that call will block until that computation is finished. To actually get the result, you can use the result method or the gather method. So result is a method on futures, future.result, pulls the data off the cluster, brings it back to your local computer. Gather can take multiple features, or even the same feature multiple times. Apparently not. And bring it back. So, slightly, if you remember the delayed example, if you were to run this in, sorry, different point I wanted to make. There's also an asynchronous compute method. So if you remember, we had daskobjects.compute or dask.compute would block. We'd have to wait until things were done computing. If instead I make a Dask object, total, and instead of calling total.delay or total.compute, I use the client, our distributed scheduler .compute. That's going to return a feature for that result while it computes the Dask object on the cluster. This means that locally in my notebook or maybe in my local process, I can be doing other work while that work is done on the scheduler and then come back to it when it's finished. If I wanted that result now, I could call future.result and get it back. So an exercise for you. Rebuild the above delayed computation. Instead of using delayed, use client.submit. A few things you need to know. You can pass, instead of actual arguments to submit, like we did up here where we passed in 1, you can pass in features instead. And Dask will schedule the computations to wait on until those are done and then run them. Cool. So I'll give you a couple minutes to finish that. Similar to delayed, instead of calling delayed on the function, we just slightly rearrange the parentheses, and we submit inc to get x, we submit dec to get y, and then we pass both of those features to submit again to call add. At this point, total is still a feature, but if we call total.result, it's going to block. And we can watch over here as things compute in our scheduler. So we still have one task processing. And eventually that task finished, and we got our result back. So this is a really nice set of tools. We also have other APIs like map and a couple other things that you might be familiar with. But this is nice for building dynamic asynchronous computations across a cluster. So instead of Dask, where you build up a graph at one point, and then you send it off to the scheduler for things to be run. Using the Futures API, you can build up graphs that change over time. You can build up computations that you can adjust as things are going. Using bag as before, I'm going to make a quick larger collection just to demonstrate another point. If we call the asynchronous compute on the client, remember this returns futures, not actual result. We can then use the progress bar widget to actually watch things compute in the notebook. So over here, we still have things computing on the cluster. This is generally more informative, but in just a notebook, you actually have a progress bar. And then at the end, after all those features have finished, you can pull them back with gather to get the result. Cool. So this is not an exercise. This is just a quick demo of a slightly more complicated asynchronous computation. This is going to be doing a super naive parallel optimization of the Rosenbrock equation. So that's just it's a common benchmark for optimization problems. The super naive optimization is we're going to iterate through, starting with a maximum number of iterations, so we don't want to go too many times. And every time we find a point better than our initial point, we're going to scale our random search slightly smaller. So we're going to start with a point. We're going to pick a bunch of random points around it. We'll keep evaluating that function in parallel. When we find a point that's better than where we initially were, we'll use that one instead, and we'll get a slightly smaller random circle around the new better point. And we'll keep going until we either converge or we end up with we've used up all of our iterations. This is not a good optimization strategy, but this does at least show off some asynchronous computation. So as things are going, we're pulling results back. We're looking at them. We're submitting new ones. Over here, you can see we're evaluating in parallel the whole time on the scheduler. But we have a loop running here, pulling things back asynchronously. This has been used in several other projects. Eric Welsh, a coworker of mine, wrote a project called Dask Pattern Search, which implements the pattern search optimization algorithm in a very similar way. That is actually a much smarter way of optimizing than this naive approach. Any questions? Cool. So there was a few other materials left in the materials folder. We had another one on storage we're not going to go over. Dask has tools for routing from different storage formats like Parquet. There are smarter ways to store things on disk. And then there's a homework notebook, which includes, notebook validation failed, includes a couple different data sets and some example problems you might want to work on your own time. Leaf page. So, and if you want to see the materials, they are at this link right here up on GitHub. Note they are not in the main branch. They are in the SciPy 2017 branch. Anyway, and we have a couple minutes left for questions. Otherwise, this concludes the tutorial.
So, do you want to comment on what's currently available and what are your thoughts in the future in terms of integrating in like an existing Hadoop or Spark environment?
Sorry, what was the first part of that question?
Do you want to tell us what were your thoughts on the current stuff that you have and what you might get in the future to integrate in Hadoop and Spark environment?
Yeah, it's a very broad question. Let's see, let's go through a bit of history. So Dask started about 2.5 years ago. That sounds right. And it was originally just a parallel array implementation. And we had no distributed scheduler. Everything was set to work just locally on disk. It was designed to work on out-of-core data sets, meaning we want to be using data on disk and only loading small bits of it into RAM to do chunked block graphs. This was first picked up by the climate science community in a project called Xarray, which is an amazing library for using data that fits that kind of model. Very powerful tool for labeled arrays. And so they've been using Dask to work on larger than memory data sets very successfully. You don't even have to know that you're using Dask at that point. DataFrame came later, and then in the last year and a half, I believe, that sounds right too, we have the distributed scheduler, which at this point is fairly solid. We have lots of nice tools for working with it, and it's being deployed both in industry and academia locally across several large clusters. I think the biggest I've heard of is 1,000 nodes. We have several ways of reading from common data formats in the ecosystem. So we can read from S3, Google Cloud. It plays well with HDFS, so we can find data that is on a node and then move the computation to the same node as the data. We can run in the cloud like that. You asked about Spark for fun and benchmark and other reasons. We have made a nice tool that you can spin up Dask clusters from Spark workers and Spark workers from Dask clusters. So if you're more familiar with one tool or the other, it's easy to set up both. Dask is a comparison between Dask and Spark. I'm not sure if that was also your question. Was that part of that?
So I use none of these tools.
You use none of these tools.
And I hate them with a passion.
Okay.
But it's just that with more and more people who, well, basically there's this tension between the fact that big companies use these tools, and some people want to use the third-party data ecosystem in there, and these tools are basically a noise in the company.
Mm-hmm.
And I know that in the Dask ecosystem, you're getting better at slotting in them. So.
Yeah, I think I understand. We try, when we're designing APIs, designing tools, to be as Pythonic as possible. So we try to fit common interfaces you're familiar with. So Dask data frames look like Pandas data frames. The extra API and the scheduler looks like concurrent.futures. So if you're familiar with working on a single node in Python, hopefully these tools are familiar enough that you can at least easily learn about how to scale up to a larger cluster. We also try to keep setup super simple. So if you're familiar with Python, we try to keep it in a way where you can set up a cluster without having to know too much about network administration. Yeah. Anyone else?
It's worth saying probably that the emphasis of Dask might be slightly different from Spark, which is become, it's not exclusively meant for business uses, but that's sort of the thing that it's been, so making large aggregations of tabular data. Dask can do those things, as you saw, but Dask exposes, I would say, the low level, the ability to make your own algorithms is much, much easier in Dask, especially if you happen to already be a Python programmer. And so novel things are likely to come out of the Dask ecosystem sooner, I would think, because to program, to make something new in Spark, you really have to get into the internals, and there's a very small pool of people that can do that.
Yeah, they're doing more than this, is that a lot of the Spark people actually end up moving from Spark to Python to Spark to Python.
Well, that's a problem in itself, yeah.
Mhm.
Yeah.
We also, just touching on that, we try to give really good error messages so you don't get some big Java traceback too. It's just Python reporting. Yeah. Anyone else? Also, just to clarify, both are great tools. I don't want to say competition here. Yeah.
Just a question. You do have an error that's somewhere in the graph. Is there an output that has like visualization of, oh, it happened in this piece of the pipeline, or it happened, like, you have the graph and it highlights the section in red where the error occurs? That would be awesome.
So, couple of things to touch on that. One, for graphs of normal size, so when people are doing computations on real work, not tutorial problems, usually the graph is big enough that graph is kind of bogs down drawing it. So drawing it that way isn't super useful. Talking about debugging, I'm going to plug my talk on Thursday again. I'm giving a whole talk just on debugging Dask stuff. But in gist, you will get, if you call compute, so it's a blocking thing, you'll get the error traceback in your process. You'll see exactly the Python trace that led to that. You can see which function it ran and what line it errored on, whatever message was reported there. If you're using the futures API, calling result will bring the same error in. So future.result, same error shows up. Cool. If there are no more questions, thank you.